All right, thanks for joining me tonight, everyone. I'm going to be talking about loops, a little bit about data flow analysis. So I assume we've all heard about loops, wildly popular construct in programming. So the idea of the while loop is that we execute the guard. As long as the guard is true, we execute the body. Eventually, at some point, we will stop executing the body because the guard will be false, which point we'll jump out of the loop. And I think it's fair to say loops are the cornerstone of imperative programming. Racket has some interesting looping constructs. We don't really need to know much for the class. The thing that we're going to cover is basically the while loop. The while loop is sort of the most basic loop. If you don't have mutability, then the while loop is useless, right? Because while doesn't really return a value. It basically, from a functional programming perspective, it reduces to void. And so while is not really useful unless you can also mutate within the loop and then look up the variable at the end of the loop, for example. And so this goes hand in hand with setbang that we talked about last lecture. But it's a pretty simple extension of our current compiler. The basic idea is that you translate while into three blocks or more, because as you're, for example, generating the header and the body, you might have to split off and generate more subordinate blocks that then come together. And so it's an interesting part of this exercise, of course, but the idea is that we generate a header, a body, and a conclusion. The header tests the guard and jumps to either the body or the conclusion based on whether the guard is true or false. The body actually goes out and conducts the body, linearizes that and generates code for it. But then at the end of the body jumps back to the header to then go reevaluate it. And eventually the conclusion gets run. It's not hard to implement this as an extension of our current compiler. The main intellectual challenge here is that we have to extend the explicate control pass to be able to sort of extend the end of generated blocks and then do interesting things with their return values, like, for example, generate code that does an if and then branches to either the body or the conclusion, or at the end of the body generates code that jumps back to the header, for example. But otherwise, it's mostly just adding extra forms to submit or to handle while. And at the end of the explicate control pass, we're in the blocks IR. And there we're just with ifs and gotos. So after that explicate control pass, basically nothing in the backend has to change, which is something that's very exciting in terms of the expressive power we've got. Another thing I want to point out very briefly is that now we've truly arrived at Turing equivalent computation. In previous projects, we were at like Boolean formulas over domains of size n. Now we're really at Turing equivalent computation, capable of expressing any Turing, any function you could compute on a Turing machine. And this is a real significant accomplishment, even though we don't have functions and closures, which will really take us to what I see as kind of like the full language. We still have something that's at least Turing equivalent. And so that's very exciting now. And that leads us into our next problem, which is static analysis. And static analysis is really the gateway to optimization. Static analysis is the problem of how do I make definitive, approximate statements about my code without running it, just reasoning over what it could do. Now, the question is, why is it bad to run it? And the answer is, in general, you can't run the code because you would need to explore an arbitrary, not maybe infinite always, but, an enormous number of inputs to really be able to cover all the interesting behavior. There are tools that try to explore program behavior like fuzzers, and they do a great job of exploring program behavior, but they often don't really get deep into the program. And so if you're trying to do optimization, you often want to do things that don't work in general, but work under certain assumptions. And if you're doing that, you need to employ some sort of static analysis to be able to make definite determinations about what your program is doing. So just to motivate us, I'm going to discuss basically common subexpression elimination. So notice how b plus c occurs 3 times. We could compute it once and then use it 3 times. And we're going to, that's going to motivate our study of something called available expressions. An expression is available when it has been computed and it has stayed the same since the last time it was computed. Not necessarily that it, the variable storing it hasn't been overwritten. That's sort of a separate question, which we'll talk about a little bit later. But it's has the expression been computed and has the value of that expression stayed the same? And so we can do this by basically associating with every statement in the program sort of two sets. We're going to have a sort of in set, which is all of the analysis facts that are true coming into the statement. Then the statement is going to make some transformations. And then after the statement, we're going to have an outset, which is a set of analysis facts that have to hold after the statement is true. Now, in this case, an analysis fact represents a available expression, a definitely available expression that has been computed and has not changed value since the last time it was computed. And so let's just look at a little example here. Now, at line 1, we are going to generate a new available expression by computing b plus c. Because b plus c will now have been computed and stored in T1, but more importantly for this analysis, computed, we know that in subsequent expressions, like for example, line 2, b plus c will be available. And later on, eventually in line 4, the hope is that I'll see b plus c being available as well. But also, as well as generating up, as well as generating up some analysis facts, we also might kill certain other analysis facts. So for example, on line 6 right here, I write 0 to a. Now this kills the availability of any expression mentioning a, because now I've overwritten a. And so if a plus 1 was valid before, which it was, I just computed it on line 5, now it is no longer available, because I have now changed the definition of a plus 1. Sorry, I've changed the definition of a, which is included in a plus 1. So now a plus 1 is no longer known. A is at 0, it's been trashed again. Same thing sort of happening here. Now, this is an interesting case because you would think I might generate n plus 1 because I just computed n plus 1, but I wrote to n. And so the rule is going to tell me that here I kill any expression mentioning n. Now, the idea is that information is going to flow forward in the analysis. So I know here on line 1 that I generate b plus c, but on line 2, because I know that I generated b plus c on line 1, I'm going to know that the flow, the set of analysis facts coming into line 2 includes b plus c. The set of analysis facts going out of line 2 is going to include b plus c and also a plus 1, because there haven't been any intervening writes to b, c, or a as a consequence of writing T1 and T2. But the interesting case is what happens in the case of joins. And so, for example, right here, from line 2, I've got the set b plus c and a plus 1. But from line 8, right here, I've only got the set b plus c. And the question is, what do I do? The answer is basically this. For an expression to be available, it has to have been definitely computed and definitely not have changed since the last time I computed it. Now, when I get to header, I'm going to merge these two different ways of getting to header from line 2 or from line 8. And the key insight is that I want to basically merge by taking the intersection of the sets. Because let's say, for example, I've got b plus c available along this path here from 2. That was available. And and it's also available from 8. But a plus 1 is only available from line 2. If I were depending on its value, well, it got changed because on line 6, I just wrote to A. And so now, coming from line 8, I can no longer depend on having computed a plus 1. All I know is that I have b plus c. And a student asked a very insightful question in class, which was basically, well, what if I tried to just consider both possibilities, right? What if I considered whether I came from one branch or the other? There is a way in which you could do that. So that is adding things like, for example, path sensitivity, which considers which branches were taken, for example. The issue with that is that you can't do it in general because you can't always infinitely unroll loops, and there will be interesting cases of that. And then second, it can, in general, massively blow up the complexity of the analysis. So here, we're intentionally considering what happens when we come from either line 2 or line 8, and to combine them, we're going to take the intersection. So that's what we're going to do here. So in this specific example, the available expressions here at the beginning are going to be nothing, then it's going to be b plus c, then b plus c and b plus a. Coming in to the loop header, it's going to be b plus c, because over here we generated b plus c, went to the header. Through here we had b plus c and a plus 1, went to the header. A plus 1 fell out because it didn't get, it's not part of the intersection of b plus c. And down here in the body, well, now we generated b plus c, but also that was true coming in. And then here as well, we've got b plus c, and then now we've computed a plus 1, right? Because we've just computed it right here. It wasn't previously available. We've computed it right here, and so now it's available, but then we reset a to 0, and so it falls out of the available expression set. And then when we go around the loop, because this is just b plus c and not a plus 1, it's not available right here. At the end of the loop, we have b plus c available, and we can use it as expected. So in this case, we can detect that this usage, this usage are both things that we could have lifted up and are, in this case, I guess they're in T1. So available expressions is an instance of a very common class of data flow analysis problems, the sort of bit vector data flow analysis problems. And the idea here is that analysis results are always sets of facts, where facts say very specific, concrete things about the program. Now, for this whole setup to work, the set of all possible facts has to be finite. So for example, in the set of, in available expressions analysis, we aren't talking about all possible expressions in the world. We're talking about all syntactic expressions in the program. Now, the program is finite. Any specific program is a finite amount of text. So the number of expressions in the program is also finite as well. And that's going to be a key thing in showing the termination of the analyses later on. Now, in each of these kinds of data flow analyses, we're going to talk about other ones beyond available expressions. There are some other useful intraprocedural analyses that fit this kind of a mold as well. But each of them defines a gen and a kill set. And then paths are combined using either basically union or intersection. And if it's union, we call it a May analysis, because it's the case that the analysis fact may have held along any of the incoming paths. If it's intersection, then it has to have held along every incoming path. And so if it's a sort of an intersection when you join analysis facts together, because remember, analysis results always have to be sets. They can only be sets of facts. And so what can we do with sets? Well, really, we can just intersect them and union them if we're thinking about what to do in terms of joining stuff together. And so, for example, available expressions is a must analysis. And so we intersect all of the potential things from different join places we could have gotten here from, right? From all different predecessors. The reason is that to be available, we had to be available along every path, right? And so, but one insight here is that for any of these sorts of analyses that are of this kind of a flavor, we can actually efficiently implement them using bit vectors. And that was one of the cool insights of this early work by Kildall and others on compiler optimization. Now, given that we have a gen and kill for each of the statements, Along with the control flow graph that tells us things like the join points, we can write out a set of the sort of flow analysis equations that talk about how to compute in and out sets, and also talks about how to propagate them by running the analysis and propagating information to compute the entire analysis to generate a solution for the program. So for available expressions, just to write it out formally, gen of an assignment yields E, the singleton set, which is the expression that was computed, assuming there are no occurrences of X in E, right? Because you don't want to kill something that you just generated. And then an assignment to X kills anything, any expression in the program that contains X. So that's gen and kill. Now, available expressions is a forward flow analysis. So what we're going to do is we're going to say that the incoming analysis facts represent, now it's a forward must analysis. So we're going to say the incoming analysis facts are going to be yielded by taking the output of all of the edges incoming into a node. So if it's a join point, it's going to be all of the different paths coming to our node, and we're going to be intersecting them together to get a set of analysis facts for that in. And then to generate the out, we're actually going to push the information forward. How are we going to do that? We're going to take our in set, we're going to subtract out everything that gets killed, and then we're going to gen in everything that this current statement generated. All right, so just looking at an example of computing this, it's always safe to, in this case, initialize all analysis results to the empty set. That's kind of the notion of what it means to be smallest in this analysis. The next step is that we're going to run the flow analysis equations forward. And so here I'm going to discover that x plus y is available, x plus y is available. Here I didn't discover anything, it's just a constant. Here x plus y is available. Here I didn't discover anything, it's just a constant. And then I can push them forward some more, so I can discover that x plus y is available at the end. Just to see a little bit more complicated of an expression, or sorry, an example, here I've got one where I generate x plus y. I would have killed anything containing A. My inset is empty. My outset is x plus y. This is the result of the full thing happening. So the interesting part is that we're merging the set coming from 2. So the outset is x plus y, a plus 1. And we're merging that with 6. The outset here is x plus y, a plus 1. These are the same set. And so when we take their intersection, we get the same thing. That's our in. And that yields the out as well. So I'll let you look through that one a little bit longer as well on your own. And this is a much larger one. I'm not gonna cover it. Let's look at, so we've talked about available expressions. I said there were more of these that fit the same mold. So another one of them is live variables analysis. And live variables asks which variables are live at each program point. A variable is live if it is used at some later point in the program path, and it is not overwritten in that intervening time. So we use this analysis for register allocation, because if a variable is live, we really want to keep it in a register because we're going to use it. If a variable is not live, then it doesn't matter if we keep it in a register or not, because it's not really going to be used, at least immediately, right? And so in this case, this is actually what's called a backward analysis, because we're going to take information as we see it, and we're going to propagate it backward through the analysis. So here I see a usage of C, and I'm going to propagate it to my inset. And then when I see B and C here, I can determine, well, that's B and C as well, and I propagate that up. Well, but because I see a write here of B, I know, well, now that's not live anymore, right? And so it's just C that's needed later here. So when I start thinking about this, I'm going to determine that this is basically sort of a backward May analysis. The gen set is going to be all variables that were read by the expression. So in this case, it would be B and A. In this case, it's B and C. In this case, it's C. In this case, it's A. The kill set is the thing on the left-hand side that's being assigned to. So here we're killing C. Here we kill B. Here we kill C. Here we kill B. Here we kill A. And the idea is that live variables is going to propagate information backward rather than forward. So now, instead of writing the flow analysis equation that said, over here, in is the intersection of all of the incoming, instead of writing that, we're going to say that out is basically the union of all of the sort of outgoing edges, right? We're going to transfer information backwards to them. Our in is going to be gotten by sort of propagating information from out, subtracting out all of the things that we were going to kill, and now generating everything from this current statement. In this case, we might ask, for example, what variables are live before line 3? So coming into it from here, we've got x and y. For example, we've got x used at line 10 and 4, right here. And then what about before line 8? Well, we know 3 is our successor, and y is used on line 8 before the assignment. So, live variables is an example of a backward May analysis where we're pushing information backward through the program. Our analysis facts are sets of variables which are potentially live. And it's a May analysis because it's, along some path in the future, right? That's when a variable is potentially used, is when it's live, right? If it's definitely not used, then it's not live, right? So we can see an example here. Here I generate y, I'm pushing that backwards. I don't kill anything because I'm just a print statement. Here I kill y, even though I gen z. So, my out is y because I push this up here, and then my in is z, which I get by pushing this z up through this statement. That goes here, but I kill the z here, and I get x, which is read from right here in statement 2, which I then push up, but then that gets killed, and my in is just y here. Right, so another example. Some more examples I have here that I'll let you browse through in your own time. But the big example, or sorry, the big observation here is that each of these different analyses are basically doing the same thing. They're iterating a set of these data flow equations until we get an answer, starting with a sort of smallest sort of initial guess. And this is going to give us a systematic recipe for how to design data flow analyses. It's not like we have to sit down and come up with this process from scratch. At least if our analysis fits this kind of framework, then we can get something in sort of a push button, sort of systematic manner. And so here's the way we do it. We pick a set of analysis facts, and this has to be bounded in practice to get termination, right? If we have an infinite set of analysis facts, well, we might not be able to compute that. So it needs to be a finite set of analysis facts. That's the kind of thing in available expressions and live variables, those kinds of things, right? And so we pick a set of analysis facts. We then also define gen and kill sets for each statement. And then we decide, is our analysis forward or is it backwards? All right. If it's forward, well, then we're pushing information from in to out and then running gen and kill forwards. If it's backwards, we're pushing from out to in. And we also need to decide, is it a May analysis, in which case we basically resolve differences by using union, or is it a must analysis where we combine and merge paths at join points using intersection? So once we specify those, once we specify analysis facts, gen kill sets, forward, backward, May, must, then we get an analysis basically for free. And so I'll describe how that happens. But before I do that, I want to give some examples of some common intraprocedural data flow analyses that fit this framework. So a forward May analysis is reaching definitions. Forward must is available expressions. Reaching definitions basically say what definitions may reach some point in the program. Backward May analysis is live variables. What variables are live at some point may get used at some path on the future. Another example that we haven't talked about, but I'll just mention, is very busy expressions. And very busy expressions is sort of expressions which are necessarily going to be used along all paths. These might be things that we could hoist up sort of earlier in the program to hope to pull them out of loops, for example. And now, of course, the whole point here is to sort of generalize, and this is where it gets all a little bit more abstract. And so we're going to use something called a fixed point. Now, in general, a fixed point is a point of a function x such that f of x is equal to x. So it has to be a function whose input and output is the same type. But the big observation, so of course when I was learning about this, the thing that was very confusing to me is that knowing that something is a fixed point is really not helpful at all unless you know what the type of x is, you know something about its type. Intuitively, I'm going to tell you, in this case, x is basically something like analysis result. And the idea is that we're going to define the analysis as a function that's going to take an analysis result, which is basically an approximation of the program's behavior, and is going to give us a little bit more information, right? It might push some analysis facts forward a little bit more. At some point, we're going to exhaust the ability to do that, because the set of possible analysis results is going to be bounded. That's something I said a few slides ago. Remember, one of the things I said that's kind of key to this process is that there is a finite number of possible analysis results. And so intuitively, the idea is that f is going to be something we're going to define pretty soon as a monotonic function. So it's only ever going to get us a little bit better and better result. And at some point, we're going to run out of ability to do that, and that's going to be when we're just done. And that's the sense in which it's a fixed point. Now, for the case of these bit vector data flow analyses that we've been talking about, x basically represents the in and out sets for each statement in the program. And particular to available expressions, x is a finite map from each statement in the program to the in and out sets, the available expressions for each in and out of each statement. And one thing that we're going to see is that whatever x is, we have to possess a notion of bottom, which basically represents no information. In the case of our sort of setup here, it's going to be the empty set. So now the question is, what is f? So a fixed point of a function, f, is some point x such that f of x equals to x. And now the question is, what is that function f? And I've told you that basically x is something like flow analysis solution. So f needs to be a function that takes us from a flow analysis solution to a flow analysis solution. The idea is basically that f is going to be a function that's going to run the whole analysis for every statement all at once, and it's going to get you a little bit better and better result. And so I can think of taking the entire analysis result for every input and output set of every statement in the program and building that up as a little data structure that I'm going to call like analysis result. And now I can define f as the function that just basically does the whole analysis result, runs one step of it. And doing that discovers some new analysis facts. It's going to turn out that the function f is always going to be monotonic. What I mean by monotonic is that it's always adding information. We're never removing information. That's going to be important so that we don't re-explore states that we've previously explored. But if we know that f is monotonic, and it will be by construction of the way that we're doing things, we're going to be able to exploit some nice properties to get some favorable implementation details, let's say. Now, if we keep computing the available expressions, that corresponds to basically continuing to run the analysis for multiple steps, where each run of that function f, remember, is over that whole analysis result for the whole program. And continuing to run it will propagate information through the analysis. And in this case, since we've got this little loop, we're going to combine the information from line 7 and from line, from the header. And we combine them, we get, when we combine them using union, in this case, it's a may analysis, we get sum I. But in any case, eventually, we keep running the analysis. We discover more and more information. We're going to get to this analysis result here. So eventually what's going to happen is things like we'll propagate up I and j, so they'll flow all the way up. J will eventually reach the header's inset and propagate all the way back out here. And we're going to get to this point that I'm called x sub n in this slide. But this point has an interesting property. It has the property that if we take the analysis and if we keep running it, now we just get the same input result back. Because we won't have any new analysis information to discover. There's no new analysis facts to find. And now we are at something called a fixed point. And this is the result or the fixed point of the analysis. At this point, no new analysis results are discoverable. And so the question is, how did that trick work? How do I make what I just did rigorous? I just described a way of computing analysis solutions. The method I presented is called chaotic iteration. And the claim that I'm going to make is that the process that I just showed, where you start with basically the empty analysis result and you just keep running the analysis, the claim that I'm going to make is that that always yields a fixed point. It always yields a point where the analysis is sort of saturated fully. It knows as much as it could possibly know about the program. And the question is, how do we make the claim rigorous? So we need a little bit more we need a little bit more formalism. So we're first going to talk about what it means to be a monotonic function. And then we're going to talk about what it means to compute via chaotic iteration. So first, I need to talk to you a little bit about a mathematical concept called a lattice. A lattice is basically an information order. It's a mathematical structure. It's a generalization in the same way, for example, that groups are a generalization, right? They're sort of an algebraic structure, and a lattice is too. So a lattice is a set E of elements that are your basic lattice elements, and you have to give a few other things. So you need to specify a partial order. So in this case, you would think for natural numbers, it might be like less than or equal to, right? And so a partial order has some properties. It has to be reflexive, has to be antisymmetric, and it has to be transitive. Antisymmetry just means if A is less than B and B is less than A, then A and B have to be equal. We also need another operation called join. So join is the least upper bound. Join is going to be the element E prime that is the smallest element such that E prime is greater than E0 and E prime is greater than E1. This is called the least upper bound. It's the smallest element that encapsulates both E0 and E1. All right, so this takes us up, it ascends the lattice. Then we've also got, I have written it wrong here. It is the meet, and I have used the wrong character. So now we've got another operation, E0 meet E1, and this is the greatest lower bound. It's the greatest element E prime, such that E prime is less than E0, and E prime is less than or equal to E1. And then we've also got two named elements. These are two elements that have to exist. One is called top, the other is called bottom. The idea is that for all E, top is less than or equal to E. And then for all E, bottom is less than or equal to E. E is less than or equal to top. And for bottom, bottom is less than or equal to E. Now, you can think of lattices as sort of a type class or an interface. Why do we care to generalize? Well, many of the properties for these data flow analysis frameworks hold over any arbitrary lattice with some certain properties. And it's really hard to build these static analyses. And so you don't want to have to build them one at a time. You want to exploit a general framework for building them. And then you want to instantiate a lattice that allows you to do some problem-specific reasoning without having to reconstruct all of the reasoning for sort of the sort of general analysis machinery yourself. It's that hard of a task if you really want to do this correctly, right? And so I want to throw out a few example lattices that will help us as we go throughout this class. So for any set S, the power set of S, so the set of subsets of S, forms a lattice. So the join is just cup, so union. The meet is cap or intersection. Top is the set S. Bottom is the empty set. Okay, so power sets of sets form lattices. Very good example. It's one that's very apropos because this is very relevant to all the analysis we've been doing in this lecture, right? Because our analysis facts are sets of analysis, or sorry, our analysis results are sets of analysis facts that we join together or we meet together, something like that. Another example of a lattice, one that probably we won't use for program analysis, but just an example to think about, is positive integers ordered as follows, where you say x is less than or equal to y if and only if x divides y. So the meet is the greatest common denominator of x and y. The join is the least common multiple of x and y. And the idea of all integers ordered by divisors doesn't really work. And so to think about why, ask yourself, what happens with less than? Is it antisymmetric, and is that a problem? There's also a lattice of 0 and 1, right? So they just form a lattice themselves. 0 is bottom, 1 is top. Min is meet, and max is join. A few others, propositional formulas ordered by logical implication. Okay, so implication is less than or equal to. Meet is conjunction. Join is disjunction. Top is true. Bottom is false. Also, the lattice of integer intervals such that A is less than or equal to B. Okay, and we're going to order these by saying that x1 has to be greater than y1. So basically, we're going to say that the interval x1, x2 is contained in the interval y1, y2. That's the ordering here. Top is negative to positive infinity. Bottom is the empty or impossible interval. And then we can join them by taking their min and max and min to meet them. Another example is the constant propagation lattice. The constant propagation lattice is basically a lattice. It looks like this. Top says it's any possible integer. Bottom says it's definitely nothing. And then we've got an infinite width of things that are basically the value exactly 0, exactly 1, exactly -1. We use this lattice when we're doing constant propagation through a program. The idea is that if we know it's an exact constant value, we can just inline it. But if it's anything other than a constant, well then, we just don't inline it. We just don't touch it at all. We let the general machinery do its job. And so the idea is, if I add exactly 1 and exactly 2, I get exactly 3. But if I merge exactly 1 and exactly 2, well, now I don't know what to do, so I have to go to top. So this is an interesting lattice that gets used a lot in doing some program analysis, and it has some nice properties. I've also written it here as something called a Haas diagram, which is a way of visualizing a lattice by writing top, writing bottom, and then here, for example, I can see the greatest, the least upper bound, of exactly -1 and exactly 0 is top. I can just see that here by seeing that this is the smallest thing that is sort of above exactly 0 and exactly -1. I can also see that their meet is bottom. And so this is a way of sort of visualizing a lattice in this kind of a manner. So just kind of wrapping up here, lattices now give us these information orders, which allow us to compare and join information together. And using lattices, I can define monotonic functions over lattice. So let L be some lattice. If f is a function from L to L, so a function that maps lattice elements L to other lattice elements L, then f is monotonic whenever it has this property that for every input E, the output is greater than the input. So that's monotonicity. It's this idea that whenever I take some function input, I had better be able to map that to something that is higher up on the information order, higher up in the lattice, so that I'm strictly ascending, or I'm equal, right? And so a monotonic function one of the things that you can think is that a monotonic function never moves you down the lattice. You're only going up, or you're staying still. If you're staying still, you're at a fixed point. But if you're not at a fixed point, you know that you're somewhere higher up in the lattice. You're definitely not lower down in the lattice if you're a monotonic function. So this brings us to the big result, and I won't formally prove this result, but it's a very important result that's worth knowing about. So here's the statement of it. Let L, with some ordering, be a lattice, and let F, which is basically a function from L to L, be a monotonic function over L. The set of fixed points of F also forms a lattice. Just unpacking that, what does that mean? Well, since the set of fixed points forms a lattice, there is a least fixed point, right? Because a lattice has to have bottom. And so because I know the set of fixed points forms a lattice, I know that there is a least fixed point. And also in particular, that least fixed point lies in L. And we can compute this least fixed point by chaotic iteration. Basically, we start with bottom, then we apply F, then we apply F, and we keep applying F until the result doesn't terminate, until we basically find a fixed point. Now, the Naster-Tarski theorem is something we're not going to prove in class. It's something that I'll define here. But one thing that is a trivial consequence of the theorem is that if the lattice L is finite, well, then the analysis definitely terminates. And here's why. If you think about applying F on bottom and apply it as many times as you could, well, because the lattice is finite and because the function F is monotonic, you're only ever going up the lattice. And because that lattice is finite, in particular, it's finite height. And so eventually you're just going to run out of L. You'll eventually hit top. And so if you make L finite by construction, then all ascending chains are also finite. There's no infinite ascending chains, which are the thing that might cause the analysis to be non-terminating. And so it turns out that, due to this very famous theorem, we can now define least fixed points as basically just the chaotic iteration of some function f, assuming that that function f is monotonic over some lattice. It turns out this is not usually what we actually want to do in practice. So this is called chaotic iteration. And one real downside of the approach is that everything from every previous iteration gets rediscovered every subsequent iteration. That's no good, right? So that's massive asymptotic overhead. And the observation is that if we exploit some properties of some of the domain, we can often incrementalize the analysis. So for example, in these bit vector analyses, we know that we're working with power sets. And power sets have nice properties that we can use semi-naive evaluation. We can only consider new elements of sets as we're pushing the analysis forward. This doesn't work for every analysis domain, like things like non-distributive domains, but it works nicely, and I'll talk a little bit more about it maybe later in the class. So when I learned all about this, I thought to myself, wow, this is really cool. It's very interesting. It gives us some very useful frameworks for doing compiler tasks like register allocation and use def chains. So we're going to talk pretty soon about register allocation, which leverages live variable analysis. So we're going to need to do a live variable analysis before we can do register allocation. But one thing that is, very unfortunate about this is that basically everything that I've covered in this lecture just offers no story for what to do with heap allocated data or pointer rights more generally. And the issue is basically aliasing. So let's say that you write to some pointer. Well, what if it overwrites some piece of data that you've got and now completely invalidates your analysis fact? That's a huge challenge. And what it means is that in practice, you often need to do something like an aliasing or a pointer analysis, or more generally, something like a shape analysis. And so this is where static analysis becomes very, very tricky and quite complex. And it's really just not possible to reason across functions in general. It's not possible in general to reason about the heap. What do you do with recursive functions, right? Because recursive functions are basically loops. You have to have some way of abstracting those to make sure you don't go explore forever. And what if a function that you call, for example, invalidates analysis facts that you're using? That's another challenge as well. So, the next step is to cover functions. And after that, we'll have some groundwork for being able to talk about at least a very small amount of maybe interprocedural analysis, something I'll cover a little bit later in the class. So this was a pretty intense lecture about sort of an introduction to data flow analysis. You should have learned about lattices. You should be able to define basic terms from lattices, along with monotonic functions and fixed points. The Kildall-style data flow analysis, by the way, this sort of line of work that I talked about, the traditional Gin-Kill data flow analysis, was sort of discovered and published by Gary Kildall, who has an interesting history and some association with MS-DOS and Bill Gates, and something that I'll let you look up. But the idea is, it's such a great story. It says, you give me basically your analysis facts. You give me gin and kill functions. You tell me if it's a forward or backward analysis, and you tell me if it's a may or must analysis. And then that gives you basically a framework for implementing these, efficiently via vectors if you'd like. And there are other nice implementations as well. It's a really nice story, and you should know about the common analyses like reaching definitions, available expressions, very busy expressions, and live variables. But you should also know, what is a lattice? Why do we care about them? What is top? What is bottom? What is meet and join? Those are the operators that allow us to take the least upper bound and greatest lower bound. And also, why do we care about lattices in the context of data flow analysis, or why did we learn about them? So the fixed point theorem tells us every monotonic function has a fixed point, and it means that if we can build our analyses as monotonic functions over basically lattice elements, we can sort of hook into this sort of rich history of results from order theory and things like that. So that's all I have to say. Pretty whirlwind lecture and very much intense stuff. I'll post a link to the slides on the below the video, and I'll have them on the website soon. So thanks for your time. Otherwise, good luck, and please feel free to reach out to me if you have any trouble understanding this stuff. Just to write out my email again, it's kkmicins@syr.edu. All right, thanks, and have a good night.